Okay. All right. So today we're talking about exponential functions and their graphs. So we're going to use the graphing calculator. Exponential functions are really easy to spot because these are going to be functions that have variables in the exponent. So these are going to have variables in the exponent. Sorry, Lord. There are a ton of applications of exponential functions. The whole next section, 6.2, is just all about applications of exponential functions. So the defining characteristic of these functions is that they will have a variable in the exponent. But what that causes is it's going to cause your graph to look one of two ways. So I'm just going to sketch a couple of little graphs here. So having that variable in the exponent, depending on what the variable or what you plug in for the variable, is going to cause one of two things. It's either going to increase really fast or it's going to decrease really fast. So think about, when you raise a number to a power, it gets big really fast. Or it can get really close to zero really fast if you have a negative number in the exponent. So when you see an exponential function, this is kind of what you expect to see for the graph. All right, so first I'm going to talk about the formal definition of an exponential function. There's a couple of restrictions on our definition, and I'll explain why those restrictions exist. So it says, what is an exponential function? What do they look like? How do I spot them? So exponential functions have the form f of x equals a to the x. So you can see we've got that variable in the exponent. And there's two restrictions on a. A must be greater than 0. So a has to be positive, but a is not allowed to be 1. And I'll explain why that is. So a has to be greater than 0 because if you have a negative number down there, sometimes that can cause issues with like the number I. You might end up with some things that aren't real, some things that are imaginary. But a is not allowed to be 1 for a pretty simple reason once you look at it. So let's imagine what happens if a is equal to 1. So let's think about what's going to happen if a is equal to 1. So if a was equal to 1, your exponential function would look like this, 1 to the x. Now let's just see what happens when we plug in numbers for x. What if we plug in 2? What's 1 squared? Still 1, right? If you plug in like 5, 1 to the 5th power, it's still 1. If you plug in 100, 1 to the 100, still 1. So if this is not increasing really fast, it's not decreasing really fast, it's just constant. So, whoa, that was like the worst curly brace I've ever written. Let me try that again. It's like backwards. All right, so it's not increasing. It's not decreasing. It's just constant. And part of the definition of an exponential function is that it must increase really fast or decrease really fast. So once you see some numbers plugged in, it's pretty easy to see why a can't be 1, because nothing happens, it just stays constant. I do have 2 more things to put on this page. So how do we know if the function is increasing or decreasing? How do we know if f of x is increasing or decreasing? It all depends on the value of a. All right, so we'll say generally, if a is between 0 and 1, so we'll write that using our inequalities. If a is between 0 and 1, then the function is decreasing. So if a is between 0 and 1, then your function will be decreasing. And if a is greater than 1, then the function will be increasing. So I'll explain why I put the word generally in there in just a minute. So generally, if a is between 0 and 1, then the function will be decreasing. And if a is greater than 1, then the function will be increasing. So I put the generally in there because we're going to see in just a minute, if you do any transformations to x, like if you put a little negative on x, that can flip it upside down, we know that's a reflection. So that can make it go from increasing to decreasing if you flip it upside down. But we'll see that in one of our graphs here in just a minute. All right, so go ahead and get out your graphing calculator and let's practice graphing some of these guys. I meant to bring you some graph paper so you could sketch these if you wanted to after that. So you might, if you want to, you can sketch them on your paper. I'm going to take screenshots of the graph and I'll put them in the notes so that you can see them later. So we have graph the following exponential functions. Part A is f of x equals 5 to the x. We can see this is obviously exponential. It's got a variable in the exponent. This is a very simple exponential function. Nothing crazy going on with the exponent. It's just x. All right, so get your calculator. We're going to go to our y equals screen. Clear out anything you got in there. Just type 5, then your little caret. We'll put you in the exponent. And then your x is right here by your alpha button. Okay. Now, if you've grabbed anything weird lately, you may have to go back to the standard window. So you can go to Zoom and go to the standard window down here. That's negative 10 to 10. Oops. There you go. And there it is. Now, this isn't the best view of this graph. You could change your window a little bit to get a better view. So you can see, like, we didn't need any of this down here. We only needed part of this. So you can alter your window a little bit if you want. I'll just show you how you can do that really quick. If you just go to Window, select, okay, well, I didn't need any of those negative y's down there. Make that 0. Maybe change your x max your x's only needed to go to, let's say, like 6. That gets you a little bit of a better view of the graph. But the standard window is fine. -10 to 10. All right, so I'm going to save that and I'll put it in the notes after class. There's our next one. You can see this one's a little bit more complicated. We've got a fraction as our value for a. Sometimes that's called the base. A is sometimes called the base. And then we're also subtracting 1 from x up in that exponent. You can think of this like in terms of those transformations we learned. Remember, if you're subtracting 1 from x, then that's going to shift it to the right 1 unit. And we're expecting this to be decreasing because our value of a is a fraction between 0 and 1. All right, so 4/5 to the x minus 1. All right, so I'm going to type it in just like they had it written, parentheses, 4 divided by 5, raised to, if you have a TI-83, make sure you put your exponent in parentheses. This is a TI-84, so it has a little bit more advanced features. It goes ahead and puts it up in the exponent for you. And there we go. It is decreasing. We expected that. All right, so let's take a screenshot of that. Any questions about graphing so far? Okay, last one. I wanted to put this one on here because it's kind of got this weird thing going in the exponent here. We have f of x equals 3 to the 2 minus x. We could, of course, rewrite this, and it kind of makes a little bit more sense to us if we have negative x plus 2. We're just used to seeing the x come first. So now that we can see the x has got a negative on it, that's going to cause us to have a reflection. So we see the base of 3, we think, okay, this is going to be increasing. But that reflection is actually going to flip it upside down. But either way you plug it in, you'll get the same graph. All right, so 3 raised to the 2, whoops. 3 raised to the 2 minus x. So we expected it again to be increasing because 3, our base is 3, but that reflection causes it to get flipped upside down. So that's why I put that little like generally in there, because sometimes weird things in the exponent can cause it to cause those rules to not be true. Okay. All right, so let's get to the most important part of today's section, which is solving exponential equations. In your book, they actually call these elementary exponential equations. That just means that these are the easier ones relative to some of the exponential equations we're going to see in the next few sections. So these are the rules or the steps for solving elementary exponential equations. There's just 3 steps. It's pretty simple once you get the hang of it. Once you do a few examples. This is something that I would definitely write on my index card for the next test. Typically, I put like 2 exponential equations on the test. I'll put like one of these easy ones and then one of them that's a little bit more difficult. Before we can solve the more difficult equations, we have to learn about logarithms. So we'll be doing that next week. So that's why we're only seeing the easy ones today, because we haven't learned about logarithms yet. All right, so step 1 says isolate the exponential expression. All right, so that means get the expression with the variable and the exponent. On one side by itself. So find the expression that's got the variable and the exponent. Sometimes you'll have 2, so you'll just get each one of those on one side by themselves. But get that expression with the variable and the exponent on one side by itself. Then step 2 says find a base that can be used to rewrite both sides of the equation. That just means make both sides have the same base. So make both sides have the same base. And then equate the exponents and solve the resulting equation. So just set the exponents equal to each other. So just set the exponents equal to each other. Typically, the hard part is step 2. But these are, I mean, that's the hardest part. It's not a difficult process. These are pretty easy. I think we're going to look at 3 examples today. We'll start off with an easy one, then we'll do a more difficult one, and then I think our last one is pretty easy too. All right, so let's look at our first example. Solve the exponential equation. One nice thing about exponential equations is that you don't have to check your answer. We're going to see with logarithmic equations, you do have to check your answer. So that's kind of nice. It saves you some time. You don't have to check your answer on these, but you can if you want to. Just plug the number back into the original equation. So we have part A, there's part A, part B, part C. 64 to the x minus 4 equals 0. All right, so we can see here's our exponential expression right here. So this is our exponential expression. So we want to have that on one side by itself. So we should move this 4 over to the other side. Just going to cancel that out. And you get 64 to the x equals 4. All right, so when you have whole numbers like this, you want to look at the bigger base, and you're going to try to say, you're going to ask yourself in your head, how can I rewrite 64? All right, so how can I rewrite 64 as 4 to some power? Because that's the base on the other side, which is 4. So you're trying to make them have the same base. So how can I rewrite 64 as 4 to some power? Sometimes these will be easy, things that you can figure out in your head. But if you're not good at that, you can just use your calculator. So just take your calculator and start checking and say, okay, well, what's 4 to the second power? Is 16. Right, what about 4 to the third power? That's 64. Right, so we can rewrite 64 as 4 to the third. Right, so when you have a whole number like this, whole numbers, start with your bigger side and try to rewrite it as the other side to some power. All right, so we can rewrite this as 4 to the third, keeping that x out there in the exponent. So all we did was we changed 64 to 4 to the third. All right, now we have some exponent rules we have to remember from way back at the beginning of the semester. When you have a power to a power, you multiply them. So that's going to be 4 to the 3 times x, which is just 3x. Right, now there's no exponent on the right-hand side, but what do I know is really up here? What's the exponent? 1. So that does not change it. If I write a 1 there, that just means 4 to the first power, which is just 4. Now I can go ahead and set my exponents equal, now that I have the same base. So just set those exponents equal. 3x equals 1. This is a really simple equation. Sometimes they're more complicated. Divide both sides by 3. So there's your answer. And like I said, you don't have to check this. You can if you want to, but you don't have to. So pretty easy. Just make both sides, get the exponential expression on one side, make them have the same base, set the exponents equal. All right, let's do, oh yeah, my bad, I actually have 4 parts here, A, B, C, and D. I like this one. This is usually the easy one that I put on the test. We have 3 to the x squared plus 5x equals 9 to the negative 3. Our bases here are whole numbers. We can see that the exponential expression is already by itself. This is the exponential expression. It's got the variable and the exponent. It's already by itself. So we can skip step 1, which means we're on to step 2, which just means make them have the same base. All right, we start over here and we say, how can we rewrite 9 as 3 to some power? Yeah, just 3 squared. Keeping that exponent of negative 3 out there. All right, so combine your exponents. We have a power to a power, so we multiply them. So power to a power multiply, so that's 3 to the negative 6. You now have the same base, so you can just set the exponents equal to each other. So like I said, last time we thought this was like 3x equals 1, it was really easy to solve. Sometimes they're a little bit harder. Sometimes you'll get these quadratics. But at this point, you've had a ton of practice solving these. You can either factor this or use quadratic formula. Either way, you need everything on one side. So go ahead and move that 6 over. You could also complete the square if you wanted to, but that would be a lot of work for this problem. We can factor this pretty easy. What are 2 numbers that multiply to give you 6, but add to 5? 3 and 2. Why not 6 and 1? Yeah. So those would add to 7. All right. So remember how we do this? We just write 2 little binomials. We put x in the front, and we fill in our factors. Positive 2, positive 3. Now set both of those equal to 0. So we have x plus 2 equals 0, x plus 3 equals 0. And there's our 2 answers, negative 2 and negative 3. So again, this is the one that I usually put on the test. I try to make it like a simple quadratic equation so then you can easily factor in your head. So keep an eye out for problems like that and make sure you add that to your list of stuff to study for the next test. All right, this is, I would say, the hardest one, just because fractions are a little bit harder to work with. You have 1/3 to the 5x plus 2 equals 1/9 to the 4th. So when you have bases that are fractions, start with the side that has the larger denominator. All right, so start or work on the side with the larger denominator. So start with the side with the larger denominator. All right, so you're going to ask yourself, all right, so my numerators match, but my denominators do not. How could I rewrite 9 as 3 to some power? Y'all just told me that was squared, right? 3 squared. So this side's going to stay the same. But I could rewrite 9 as 3 squared. What about this? Could I write 1 squared here? Is that going to change anything? No, that's fine. 1 squared is still 1. That's important for my next step. All right, so since my numerator is being squared and my denominator is being squared, I can sort of factor out that squared. I'll show you how you can write that. So you do like big parentheses, this is all being raised to the 4th. And then inside here you have 1/3 squared. That just rewrites it in the form where you have a power to a power. Now you can easily combine those exponents. So we just sort of pulled out that exponent, we factored it out, kind of like using the distributive property in reverse. Now we're going to combine our exponents. We have a power to a power. So go ahead and multiply them. 2 times 4 is 8. Now I have the same base. I can just set my exponents equal. Okay. So set your exponents equal and solve. 5x plus 2 equals 8. Subtract 2 and then divide by 5. So you get x equals 6 over 5. All right, any questions? How do we feel? Is this okay? The more you do them, the easier you get. I know I say that with everything, but you start to sort of get in the pattern of making both sides have the same base. You'll see a lot of the same numbers. You can obviously see we've seen 3 and 9 several times. Last one, and this is another easy one. I think I've done every problem from the homework. I think that's why I threw this one in here. I was like, well, there's only one more problem, so I'll just do all of them. So we have 1,000 to the negative x equals 10 to the 8x minus 14. Oh, and both sides had an exponent that was a variable. That's why I put this one on here too. All right, so we have whole numbers here. Start with the bigger side. Say, how can I rewrite 1,000 as 10 to some power? 10 to the 3rd, yeah. So we're going to rewrite 1,000 as 10 to the 3rd. Leave that negative x on the outside. Right-hand side stays exactly the same. Again, if you didn't know that off the top of your head, that 10 to the 3rd was 1,000, you can check that on your calculator. We got a power to a power, so you multiply them. So we have 10 to the negative 3x equals 10 to the 8x minus 14. Got serious over there. All right, set the exponents equal now that we have the same base. negative 3x equals 8x minus 14. Sometimes we get weird answers on these, that's okay. Divide both sides by negative 11. So you get x equals 14 over 11. And why is it positive? Yeah, you have the double negative there. That's probably where the two ways people get these wrong is either they completely forget how to do these, or they just make a really simple algebra mistake like forgetting to do the negative, like forgetting to divide by negative. So just be careful whenever you get to the actual solving part. Take your time. All right, so that is everything for today's section.